Hi, so I'm Marvin Lavechin, and I'm going to give you a quick overview of our work, Brouhaha, multitask training for voice activity detection, speech-to-noise ratio, and c50 room acoustics estimation accepted at ASRU 2023. So our work starts from a very simple observation, which is that noisy and reverberant speech impede the performance of speech processing systems. So for instance, here you have a graph showing the word error rate obtained by a speech recognition system as a function of c50, which is a measure of reverberation. So it is quite clear that the system exhibits very good performance when being presented with speech segments with no reverb. And on the contrary, when being given highly reverberated speech, the system registers a degraded performance with the word error rate going up to 100%. So similarly, here you have the diarization error rate of a pre-trained system as a function of the domain on which the system is applied. So again, the system registers degraded performance on domains that are typically noisy and or reverberant. So we know that noise and reverberation are important when applying any speech processing model, but how does one can tell whether speech is noisy or reverberant? So actually, this is quite hard to tell from the signal alone, as most of our degradation measures are defined before the transformation. So for instance, computing the speech-to-noise ratio requires to separate the speech signal from the noise signal. In a similar fashion, reverberation measures typically require to retrieve the room impulse response from which we can measure the strength of the reverberation. So here you have the example of the c50 measure computed on the impulse response as the ratio between the energy of the early reflections and the energy of the late reflection. So one way to measure the strength of the signal degradation is to follow a data-driven approach in which we first contaminate clean speech segments with some degradation with strength S. And then we train a neural network that, being given the degraded signal, is trained to predict S. So this is the approach we follow in this work, and I will now present our contamination pipeline. So we first start from clean speech, from clean segments containing both speech and silence. We choose a random impulse response to artificially contaminate our segments with reverberation. And in parallel, we randomly choose a noise segment that we also reverberate with another randomly chosen impulse response. So once we have our two reverberated segments, we add them together with the target speech-to-noise ratio. So this gives us a segment containing both speech and non-speech contaminated with noise and reverberation. So for any segment, we know when there is speech, the strength of the reverberation, such as measured by the c50, and the strength of the background noise, such as measured by the speech-to-noise ratio. So we can attempt to predict these quantities. So to run this pipeline, we need a data set of clean speech segments. So in this paper, we decided to work with LibreSpeech, which is a data set containing 1,000 hours of English read speech. We also need a data set of room impulse responses to simulate reverberation. So here we work with the MIT acoustical reverberation and the EcoSIF data set. So combined together, these data sets contain 385 impulse responses from everyday life locations as well as unique places. So for instance, you have impulse responses collected in the Geisel Library in San Francisco, from the Batcave in Los Angeles, or from a bar in Montreal. So the last missing component to run our contamination pipeline is a noise data set with which we're going to simulate background noise. So here we use audio set containing various noises, and after filtering out human vocalizations, we end up with 1,500 hours of noise segments. So here I'm going to play some audio examples generated using our pipeline. So an example of high noise, high reverb audio.
And to declare her issue illegitimate. He recalled to his memory that a little after her appearance in the English court, some attachment had been
High reverb, low noise.
And I make no doubt that she'll be an excellent wife for him. Ah, said Mrs. Loveday in a warning tone. Courting? Why?
Low reverb, high noise.
On the contrary, her eyes glistened, and she appeared to be suffering from violent nervous irritability. Oh, Dear grandmother, are you...
And low reverb, low noise.
Theodosius, the boy emperor, and his three sisters Pulcheria, Marina, and Arcadia.
All right. So for the model in charge of predicting the strengths of the background noise and the strengths of the reverberation, we use the following architecture. So we first have a SyncNet that learns filter features. It is followed by a stack of LSTM layers and a feed-forward layer. And at the end, we have 3 heads that take the form of feed-forward layers. So one to predict the C50, one for the SNR, and we also have one for the voice activity detection task, which pairs well with the SNR and C50 estimation task. Plus, it is quite convenient to have a single system that predicts when there is speech and the signal quality of this speech. So the model is trained jointly using a binary cross-entropy loss for the VAD objective and mean square error losses for the SNR and C50 estimation objective. So let's get through the results. So here we evaluate Brouhaha performance on unseen synthetic data, so generated using our contamination pipeline. So we obtain a F-score of 93% on the VAD task, a mean absolute error of 4.1 decibels on the SNR estimation task, and 3.5 decibels on the C50 estimation task. So the system seems to do pretty well on what it has been trained for. So in the paper, we also show that the multitask training regime is beneficial for the performance of the model. So when turning off one or multiple losses among our 3 losses, we observe a performance loss. So in other words, the best performance is obtained when all 3 losses are active. So here we compare Brouhaha on the SNR estimation task with 2 other systems. So the first one is a simple heuristic that estimates the speech power as the mean power of speech frames within a 6-second window. And similarly for the noise power. So this is a rather standard approach to estimate the SNR, which requires to have access to the VAD labels. And the second system is a pre-trained model published in Interspeech 2020. So here, the results show that the pre-trained model of Lee and colleagues seems to struggle a bit, generalizing to our synthetic test set, as shown by the high mean absolute error. The heuristic does a bit better, but the mean absolute error remains quite high, and the best performance is obtained by Brouhaha with a mean absolute error of 2.3 decibels. All right, so measuring performance on synthetic data is interesting, but it doesn't tell us if the model can be used in real-life settings. So how can we check that? So it's actually quite easy to check for the VAD task, as we have plenty of data sets annotated for this task. However, it's a bit more complicated for the SNR and C50 estimation tasks. So because we typically don't have access to the gold measures. So as we'll see later in the presentation, one workaround may consist in simply checking whether the SNR and C50 measures returned by the model capture interesting behaviors of pre-trained models on real data. So from now on, we will only consider real data that are naturally noisy and reverberated. So here we compare Brouhaha with the state-of-the-art voice activity detection system, Pianot Audio, on the baby trained corpus, which is a data set of naturalistic recordings collected through child-world microphones across 10 languages. So this data set is quite noisy and contain child and adult speech, near-field and far-field speech. So the results indicate that Brouhaha is slightly behind Pianot Audio on baby train, although the performance of Brouhaha remains competitive. So we interpret these results as evidence that training a VAD on artificially contaminated red speech is not optimal to obtain a really competitive VAD system, which is unfortunate, as audiobooks were the only source of clean speech data available in sufficiently large quantity to run our contamination pipeline. So to evaluate Brouhaha performance on the C50 estimation task, we used the But Speech database. So this consists of LibreSpeech test clean utterances retransmitted by a loudspeaker in 5 different locations, so like offices or lecture rooms. And all of it has been recorded with 31 microphones. So here you have a map of the room along with the position and direction of each of the 31 microphones. So what's good is that for each room, we also have the impulse responses from which we can calculate the real C50 and compare it against the C50 predicted by Brouhaha. So here you have 1,000 utterances randomly sampled from the But speech database. So we observe a strong correlation between the real C50 and the predicted C50 with a R2 of 0.85 and a mean absolute error of 1.1 decibel. So again, we are trying to know if Brouhaha returns useful SNR and C50 measures. So here we look at whether the predicted values can be used to investigate speaker diarization systems. So for this analysis, we compare the errors made by a pre-trained speaker diarization system against the SNR and C50 predicted by Brouhaha. So here you have the SNR and C50 distributions at the frame level as a function of whether the pre-trained system identifies the right speaker in blue or a wrong speaker in red. So we observe that the system is more likely to fail on low SNR frames, and on the contrary, the system almost always returns the right speaker on high SNR frames. As for the C50, the system almost always fails on low C50 frames. We have a peak of success at around 20 decibels, but then a higher C50 won't be predictive of whether the pre-trained system succeeds or fails in identifying the right speaker. So for this last analysis, we look at whether the predicted SNR and C50 can be used to investigate the error made by an automatic speech recognition system. So we run a similar analysis using the Whisper large automatic speech recognition system on the seedlings audio corpus. So here we have 800 utterances for which we compute the percentage of words correctly transcribed by Whisper. And we observe that the lower the speech-to-noise ratio, the lower the percentage of words correctly transcribed by Whisper. So on average, Whisper correctly transcribes 90% of the words on high SNR utterances, but this number goes down to 50% on low SNR utterances. So the trend with respect to C50 is a bit less clear, although Whisper tends to make more mistakes on low C50 utterances. So to summarize, we have shown that Brouhaha achieved high performance on the VAD task on artificially contaminated data. However, it was a bit behind P&Audio, a state-of-the-art VAD model, although Brouhaha achieved reasonable performance. As for the C50, Brouhaha seems excellent to predict it. So we've shown a slight effect of predicted C50 on the word error rate and diarization error rate obtained by pre-trained systems. And as for the SNR, we haven't found a way to evaluate it thoroughly against the gold measures, as we typically don't have access to these measures, but any suggestion is more than welcome. So for the SNR, we also showed that there was a strong effect of the predicted SNR on the errors made by a pre-trained speaker diarization and speech recognition system. So there exist many directions in which we could extend this work. So for instance, we could try different architectures or different data sets, so especially to try to improve the performance on the VAD task. We might also explore other measures to predict, so like reverberation time, intelligibility, or human-assessed quality rating. So what I think is great about Brouhaha is that it can be used in many ways. So as we have shown, it can be used to investigate the performance of automatic speech processing systems under challenging recording conditions. It can help us to develop strategies to improve the robustness of our systems. It might be used to clean large audio training sets by removing noisy or reverberated segments. And we might imagine other applications that may consist in building systems that do not return poor output or poor transcription when being presented with noisy segments. So finally, Brouhaha is available on GitHub and Hugging Face, on which you'll find the few lines of code to run the model. And thanks a lot for your attention.